Okay, so I want to make a video on this page just because this is all kind of madness here. So we're going to start off with, at the top here, talking about just what this is all about. So this is one of those things where it's like you forget the basics because you're going through all this madness and you look at a simple reaction like this one at the top here and you're like, well, what is happening? I wonder if I could just use this to point to things. Okay, so yeah, so you look at something at the top here and I'm like, I don't know what to do with this HI here. And what you have to keep in mind is that when you look at something like this, remember, your end-all be-all is when you remove a double bond, which was here, when you get rid of that, when you break an alkene, you're going to have a positive charge that appears on both sides of that double bonded bridge. And we have a decision to make. And remember, the question we're always asking ourselves, it's hydrogen versus positive charge. Where do we put the positive charge? Where do we put the hydrogen? And that's when you want to look at your carbons and see what is attached to more carbons, because tertiary is going to be stronger than secondary, which is going to be stronger than primary. And that stability is where we want to put the positive charge. So when we're looking at this, we know that this carbon is the more stable one because it's attached to 3 other carbons. That's where we want the positive charge to go. So what does that mean? That means, and we're adding HI here. So we're going to put the hydrogen on the less stable carbon, the one that's only attached to 2, that's secondary in this case. Well, what do we have left? We have the iodine. So we don't need a positive charge in this case because we can use the iodine to neutralize this charge by putting this pair of electrons here, putting the iodine here, okay? That is why this is the major product. That is the one that is formed faster, and it is the one that is more stable, so it is going to be favored. And as we see over on the right here, that's why this is a major product, okay? You might be asking yourself, why is there a minor product? Why are we forming something else? The minor product I drew out for us down here, we're just switching our decision making. We're saying, well, I'm going to put the hydrogen on the more stable carbon. I'm going to put the iodine on the less stable carbon, okay? Well, how do we know that that happens? How do we know that there's a major product, minor product? It all has to do with the stability of the carbon. So remember when we were talking about this carbon is tertiary. I'm just going to put a 3. That's tertiary because it's attached to 3 carbons. This one's only secondary, but they are only off by 1. They are not different enough for one product to really be the only thing that's formed. And this is where we get into something that's called regioselectivity, okay? So these are not, or they are less regioselective, okay? Something is more highly regioselective when there is a bigger difference. In other words, I think it's when you have a primary and when you have a tertiary. That tertiary is so much more stable. That primary really isn't going to be receiving anything, and you're really just going to have one product. That is what comes into play in a second. But real quick, while we're looking at the top here, remember that these are constitutional isomers that we're forming. These two products have the same chemical formula. Constitutional means you're removing this iodine, you're pulling the iodine and the stick, the electrons, and you're sticking it somewhere else. That is a constitutional isomer, and that's what we're working with here, okay? Okay. Now, there's another example here, this cyclohexene here at the bottom. You can do the same thing. When you get rid of your double bonded bridge and you have a positive charge potentially on either this carbon or this carbon, this one up top, this one at the north here, is attached to this methyl group. So it's attached to 3 carbons, which makes it tertiary. And the other option here is only secondary. It's attached to this carbon and this carbon. Okay, those are only off by 1, so those are close, and that means that they will have a major and a minor product that are formed. How do we know the bromine goes up north? Because it's the more stable location, meaning we're going to put the hydrogen on the least stable location, which is, if my eraser would work, why we're putting the hydrogen here, okay? Also keep in mind that this makes sense when you think about it, because we're working with halogens here. Halogens are very electronegative. They are electron hogs. So what is going to happen is that this iodine, or this bromine in this case, it's going to pull negativity towards itself, which means it's going to make whatever it's connected to, in this case, this carbon, actually more positive. And in this case, more positive is going to make something less stable. Let me think about this for a second. It's going to make something more positive. That actually doesn't make logical sense as I'm talking about it. So let's abandon that train of thought, because that would mean that, you know what? Iodine, it would make it, right, it would make it more unstable. So yes, so if we put the iodine over here, it is going to add instability. However, this tertiary carbon is the more stable one. If we're going to add something like iodine that's going to affect our stability, that's going to make something more positive, well, yes, we do want to put it on the carbon that is more stable. So that line of logic actually does make sense. That's another reason why we want to put the iodine here, because they're going to stabilize themselves. We have a positive carbon, we have a negative iodine. They're going to stabilize each other. The iodine will pull the negativity off the positive, making it more positive, but that's okay because this is a tertiary carbon. It's going to be stable. Okay, that does make sense. All right, moving on to this stuff down here at the bottom. It's really just what I was talking about here. These are just other examples. You see here, we have a tertiary candidate on the left side of our bridge, and we have a primary candidate on the right side of the bridge. Those are off by a lot. There's a big difference between primary and tertiary. In that case, the tertiary, the more stable carbon, which is this one, is going to be the only product. This is so unstable that that's really not going to form. And that again is regioselectivity. So I'll write that again. Regioselectivity is when you have a big difference. For all the examples that I've seen, it's when you have a tertiary and a primary. You have a tertiary and a primary, only one product. Regio sounds like Regis Philbin, God bless his soul. All right, only one. There's only one winner of Who Wants to Be a Millionaire. All right. Only one winner of Millionaire. Okay, so when you have that difference, when you have a tertiary versus a primary, there's only one product. You have it right here. That's going to be more highly regioselective. When you have something like a secondary and a tertiary that are only off by one, you're going to have your major product and your minor product form. Okay, and there you have it.